With us today is Colin Cooper from Colin Spatial. He's going to talk about Topobathymetric Lidar solutions.
Well, first off, this has been an exciting day, and thanks for the opportunity to allow me to speak here. I'm excited to be here. My name's Colin Cooper. I'm a technical domain expert for Colin Spatial, now NV5. Been here for 15 years, starting with watershed sciences, working on LiDAR. And just to update my profile pic, which is also probably 15 years old, here's me enjoying the Oregon coast with my daughter, Ruby. That is, that's me in a nutshell. I enjoy long walks on the beach and a Frisbee. But I have a lot to go over today. And so here's a quick agenda. I think I'll speed by the Topobathymetric Lidar technology overview, cover a couple key things there, get into the product list that we do and how we start to fuse it with other data sources besides just the green laser, and then cover river application stuff we can do with the Topobathy data, and cover like broad area and marine applications. So I always like to kind of start with this. This is the easiest way to kind of describe the differences between survey with near IR and survey with the green laser. And so if you were just flying a string with near IR, you can see that your area of interest is a big black hole. So, Topobathy LiDAR is all about adding in the green laser. That wavelength penetrates water, and you start to map the underwater topography. So if you round out your full data set, it's all about that seamless resolution elevation data going from land into water. Again, this is a typical setup. A lot of these scanners are circle scanners with the green wavelength. Won't talk too much here. I think the thing to note is there's a backscatter, and that'll come up later. See if you guys can catch it on things you can do with backscatter besides just the bottom. So just another shout out. I think you see where it sits in the larger scale things that we've been talking about all day today with the 3D nation concept. It's a large component of territory out there is underwater. So it's pretty critical to that objective to start bringing in technologies like Topobathy LiDAR. Yeah, why do it? I think I don't really need to cover this. We covered so many different applications on what you do with this data, getting that near shore gap filled in, connecting the land to where you might have sonar data, getting systems where you couldn't previously reach before. That are difficult or dangerous to get into. So it really opens that door. You can target smaller reaches with this technology, and you can do whole watersheds and whole coastlines. So it's a really complementary technology. Really quickly, these are the 3 sensors we've been using as a company. The first 2, the Regal 880 and the Chiroptera, are really shallow water systems. And I say that because they're high pulse rate, and they can kind of discern that vertical discrimination in shallow areas when you want to get up to the land-water interface. The other systems are the deep water system like the Hawkeye, which we also operate. That's a lower pulse rate because you're going to put more power to that pulse to try and basically get through the water more so you can get greater depths. So there's a lot of operational considerations here. We have everything that you have to deal with topographic LiDAR, and then we're adding in some key elements here like water clarity and vegetation that I've been talking about. You'll see that the plane is a lot lower in the diagram. To get as much energy to the water column so you can get through it and get bathy returns, you're going to fly lower with these systems. So it's going to take more lines. It's harder to plan. It's going to cost more. Things like leaf on, leaf off. That sounds pretty standard. I think we run into that a lot with riverine systems as something that to take in consideration. They're kind of contradictory conditions sometimes in Topobathy. You want to get that bank discerned. You want to get the terraces mapped, but if your leaves are on, you're not going to get through. Likewise. Once they fall off, you might have tannins in the water, or your flow levels might be higher due to the seasonality of it all. So it's a really, really tricky window to try and get in with these systems. So like mentioned, water clarity is obviously, we talk about that all the time because it is like one of the most important things when planning and designing that. And we'll talk a lot about that and different things that we do. But yeah, how clear is it, right? And along with how reflective is the bottom, that laser pulse needs to make it through the water, bounce off the bottom, and make it all the way back to the plane. So there's a lot that goes in there. Vegetation, you're not going to fire a laser through a brick wall or a mat of veg. So those are all things that we have. Honestly, they're the stuff that makes it really difficult. So to quickly cover, I'll just kind of cover one aspect of processing I think is a huge a difference is refraction, correcting for that refraction. So when that laser source is entering the water column, it's slowing down and bending, and you need to figure that out. The laser doesn't know when it hit the water. You have to basically tell these systems that. You have to figure it out, either using the IR or the green laser itself. So I kind of just wanted to show what do I mean by that. And if you look at the bottom picture here, I think I got it. Now, if you were just to refract with a flat surface, what you're going to end up seeing is these wave heights are going to propagate into the bathy bottom model. You need to actually capture the wave height with that. And you saw the circle scanner I talked about, and this could be one flight swath where the forward part of that scanner and the backward part can be, there are a couple hundred meters apart on the ground when you look at that field of view. And when you're flying 140 knots, that can be about 4-second difference from when your next point from the forward meets the back. So you need to separate that out and make sure you're doing coincident laser sources and processing. And it can have an effect. If you don't do it right, it can lead to a noisy data set. If you're going to ground it, you might be grounding the waves. So you need to get that right. We spend a lot of our time fine-tuning water surface models. Streams can be difficult as well. You might get no water surface from the green or the near IR. So, how do you handle that? We do a lot of synthetic water surface modeling, and sometimes you just need to fit a plane to make sure you're actually capturing everything you want to refract. I think that becomes critical. Here's a shout out to the Niobrara River. That is the project we've been flying for USGS, and you can see how complicated these stream systems can be. Here's a super shallow system, braided. There's sandbars with water going through them in and out, wet sand. It's really complicated. I mean, just imagine trying to put break lines here or figure out where all the water actually is and then refracting it. So you got to think about how accurate can you actually get and to refract it all. Is it worth refracting 5 centimeters of depth? There are things to consider here. So I guess I'll just start with some pretty pictures. I think this is just a stream system. So, we fly big coastal projects for NOAA, but then primarily we fly tons of rivers. I think we fly over like 25 river projects a year for the last couple of years. So we're out there collecting as much as we can, the good and the bad and the ugly places. We'll try and figure out what can work and what we can accomplish. So this would be a normal, if you're flying a USGS back hydroflattening, these would be the break lines. And I think when you add the topobathy, the whole point is you're starting to reveal all of that characterization of the channel bed and how that can impact all your models. And another thing is you are getting, there is the topo part of the bathy. Some systems rely on the near IR, but the systems that we use, a lot of these rivers are the Regal 880, and you have beam divergences on these systems. And since you're flying so low, even though you have a wider beam divergence, it's actually just as accurate as flying a 1560, like 2,000 meters above. So you can actually get point cloud, data-rich point clouds in both green and near IR on topo. And I think just illustrate the density of points you can get and the pointing angles of these systems you can get under veg, and you can really, get that transition mapped accurately. Speaking of accuracy, is quick. We talked about how do you do it? Can you safely do it? I think this is safe. This is our flight operations manager, Scott. He's like 6'4". He's out there collecting points to try and characterize how well we're doing. And oftentimes we're under 10 centimeters RMSE when we go to compare to these points. And this is just an example. A lot of our work is to replace, interpolating from cross-section to cross-section down a stream to get a model. And you can see just we can cut cross-sections and have a magnitude of density of points greater. And it's hard to quantify these data sources, whether it's sonar or weighted transect, because they're different. They're different resolutions. They're different uncertainties. So it's always something to take into consideration. Someone might stick to a rod and it might sink in a little bit, or they're on a rock feature that's small. There's so much that goes into this uncertainty. But here's a product list for the products that we deliver. And obviously the main product is the seamless elevation model that everyone uses. But we do the full point cloud. We try to adhere to the Topobathy domain profile as a standard. Even non-USGS NOAA clients, we steer them to that, with the idea in mind that someday this data might end up mingling. So there's always full waveform availability with these systems. I think Jeff alluded to, opportunity there. We've used it to extract more depth from the waveform in noisier environments. You can start to do waveform averaging to start to improve classification routines as well. So intensity images for this talk are pretty important. We normalize our green for depth, so to correct for that attenuation of the laser in the water. But you also have near IR in green, and I think that can potentially lead to vegetation mapping when you think about that on some level. And maybe I'll talk about this later, but Regal actually takes the same laser source from the 880 and puts it in a 1560 for one of the channels to try and start getting that vegetation health and mapping. So, as a product, you can have a green and near IR set of intensity. So pretty cool for all these routines that everyone's been discussing today. Water's edge break lines are pretty standard. Where's the water? That helps with a lot of things, having that shape file. And then I think void areas, you don't want to just interpolate over a void area. You might have got a void area because it's deeper, right? So it's important to map those and clip them out of your model, or come up with some plan for how you want to treat them. So here's an example of that data fusion with RGB, kind of pre-sonar integration. And you can see these triangles I was talking about. So this is unclipped, and it's just here to show like what would happen. You're not really accurately representing that stream channel. So do you have sonar to fill it in, or do you need to create a hole? And I should say, these sources that I mentioned, imagery, a lot of times you're co-acquiring photos, and you might, you're steering your operations to successful bathy, so you might not be planning solar angles, but you can still get high res photos because you are flying so low. You're flying 400 meters, so you're getting 10 centimeters or less photos. And at the end of the day, no one really turns those away if they can use them. And I threw, I don't have thermal on there, but there's also thermal. We're looking at updating our heat source modeling using thermal cameras and Topobathy data to improve those modeling opportunities. So that void layer, I just kind of want to go over. This is another project we did for a whole bunch of stakeholders, including USGS. And so this is the AOI with that imagery I was talking about. And with the LiDAR alone, we did a very successful job getting in spots you might not want to go with the boat, really shallow around the rocks, and we got that covered. But then there are these deeper areas that we need to fill in. So one of the cool things you can do, if you're lucky, you can fly the Topobathy first, map these areas out, provide them to the sonar crew, and they can go target their areas and cut down on their costs. And in this case, we had the Army Corps and the Yurok tribe out there doing sonar to fill in these gaps. And this is kind of what it looks like. They go out there and they help create that seamless model. There's obviously a lot of considerations to think about in terms of accuracy standards. And, you know, in an ideal world, you're flying with low water levels for bathy LiDAR, and then a little higher for sonar, so you can make sure you have that overlap. So that was the data. We've processed it, say we delivered it, or what are we doing with it? And so I want to just cover some river analytics, how we use it for, you know, stream restoration, for habitat, suitability, those sorts of things. And of course, inundation modeling was a big one. And there is a whole wealth of riverine applications, and they're now available beyond the traditional near IR survey approach, particularly in reference to the fisheries and in-stream habitat, where you can now map and quantify features such as coarse woody debris and submerged vegetation. We can also start to apply some of the fine-scale geomorphic classifications to entire river systems, which was never really feasible for a couple of reasons with traditional field surveys. So these analyses are, you know, they're objective, they're reproducible. So, you know, they're very good at supporting restoration monitoring and your management activities in that sense. It also, I think we've made it pretty clear, everybody, that it can support high resolution inundation modeling, and it's going to range from simple flooding scenarios to more advanced hydrologic modeling. And here you can see both coastal and riverine applications. So, you know, understanding where the water is going to go has obvious value. So I'll just start this quickly, and this is just an example of things you can do with the stream. So we have normalized the terrain elevation to the water surface, so we can iteratively raise the water level to see how the different areas are impacted. We can quantify connectivity of off-stream habitat, the different discharges, or assess the breach potential of levees and dikes. So, you know, it has a lot of implications, even for, you know, assessing infrastructure, develop properties, support insurance and risk mitigation, all those sorts of things. So a big one I think we talked about is, you know, multiple acquisitions. You know, you can start to do change detection, you know, accurately map erosion, deposition, overall sediment dynamics. So here's some examples of that on the Tunkhannon River. We actually have another contract as well where we've been flying the same system for 5 years to track sediment movement and support habitat assessment, and we've signed up for another 5. And it, you know, a big thing with we do this for a couple of projects, and it brings up accuracy and standards and how to set them up, right? Are we going to, you know, we need to be absolute accuracy, and ideally we don't build a local reference frame, though we've done that. So when you go and repeat, you're kind of forcing it to some survey point you took years ago, which could have implications. So, you know, getting that set up as we move forward is hugely important, and I'll probably talk some more about that, because, you know, do you want to be relative to the previous collects, and how do you wiggle in that environment where, you know, potentially every centimeter counts. You know, a centimeter for a client can be tons of earth that they might want to move, or, you know, there's just a lot that goes on to the centimeter scale. There are implications for using this data to support infrastructure planning and design. This could be for site characterization for dredging, like was mentioned. We've flown several dams, both for, you know, support dam operations and also to support dam removal. So, you know, how much water are we going to release? Where is it going to go? That sort of stuff. Here is an example. The upper right is that Klamath River reservoir where we had to use sonar to complete it. And you can calculate dam values at different water levels. And a really interesting application that's pretty neat is mapping lake volumes in Alaska to mitigate the impact of ice road construction and help out with their processes. So pretty neat. Again, so now we'll move into the broad and coastal applications, and I'll just kind of cover some primary objectives, which I think actually, you know, Mike alluded to that and explained quite well, and then kind of look ahead to like how does this affect things like land cover that, you know, everyone's been bringing up all these different applications, and it's been exciting to see, and we'll talk about a couple of that. You know, starting with the shoreline, I think we'll start in North Carolina. This is NOAA work to support the Florence supplemental. And I just want to cycle through, and I guess it's kind of pretty pictures, but these are data sources we collected for the project. And the photos are tremendous, and you can start peeling away those to look at the underwater topography. And you really start to understand how much elevation matters. And I think it's, if I can zoom on here, it's really cool geomorphology. So, you know, when we talked about supporting coastal geomorphology applications, this data has tremendous potential there. And I think there's just a cross section, it's about 3.5 meters deep. And a big thing about this project and almost all the projects I'm mentioning for NOAA, they're all kind of being retrofitted to support this 3D nation concept, to integrate in with USGS, to retrofit the data to also serve that community. And so they've been aligning their standards like that's been discussed, and it's a huge part of what we're doing. And I think this was showed before. I also was really interested in this as well. So this is just a coastal flooding sea level rise viewer, and I think I'll play here. And I just the example of, yeah, I think I went up to 6 feet. I guess I think a fathom was like a seafaring term for me, and I guess socially distant too. But you can see, you know, the impact, and you know, this increased resolution is going to get into a lot more nooks and crannies. It's going to probably show you things that obviously coarser elevation won't show you. So again, in addition to the emergency response, you know, the primary purpose is the shoreline. And so just really quickly, you know, there's kind of two shorelines. There's this higher resolution vector product. But I want to tie this into how this supports our other stakeholders and how it might support 3D national terrain model. So the shoreline, you know, it really, you know, it comes from NOAA, and if the retrofit this for USGS, you know, there's two different purposes. NOAA is for navigational, USGS is for hydromodeling. So this is in the Florida Keys, and I just wanted to highlight some differences. And if we directly apply the NOAA shoreline to flattening requirements to the USGS base spec, you end up with a lot of small channels and other areas that are flattened, are below the flattened ocean, resulting in sinks. So you have to augment that, connect the ocean, even the areas that are even typically below the US specification. And so that's part of that process. And this kind of leads me on to the NHD, the National Hydrography Dataset. So wanted to talk quickly on, you know, the ability to improve the stream and surface flow by incorporating topobathy. There's a lot of talk about how the resolution is being upscaled, right? There's clear guidelines now to move the NHD from the neighborhood to street level, right? So doing that, I think topobathy can help. You know, the magnitude of the information being extracted and all this needs to be automated, or else it's going to be cost prohibitive. And so I think, you know, using the shoreline, which is a requirement for NHD, is hugely important. So there's a direct connection right there. And how do we improve that? And this is, I talked about the backscatter before. You know, if you have green laser, you can obviously subtract it from the green, and you can start to see where water bodies are, right? And this can be done even if the bathy bottom is not found. So if you get a little bit of water penetration, that's going to show up in that subtraction model, and you're going to be able to detect more features. So the channelization is more present, and you can use it to your advantage. And I think I'm going to skip this. I'm getting a little late. So again, I was overwhelmed by all the stuff I saw today. I think a big challenge is how do we get this data into all these applications and tools that are everywhere. Here's just the CCAP, and I just bring that up because that we're going to extend land cover and land use right underwater, and so I kind of want to go into that quickly. And honestly, I'm out of my wheelhouse a bit here, but I did want to cover analyses that we're doing regarding land cover. We're doing broad scale, high resolution land cover land use maps for water districts. So the quote you see in the corner alludes to underestimating flood risks due to Hurricane Harvey, which NOAA collected data for in support of relief there. And elevation alone doesn't paint the picture. You need to know where water can and will go during storm events. So this is especially devastating when the terrestrial flooding meets up with the storm surge during a hurricane. And so what I'm showing off here is kind of we do our deep learning AI routines and computer vision to map these features out. And the land cover can be extended to land use. Oftentimes it's not sufficient to know what is present, but rather we need to be able to put context to some piece of information and explain why something is there. So extending land use or land cover to land use allows us to put that context of how people are actually manipulating their landscapes. And integrating this land cover, land use into existing frameworks for flood modeling can complete the picture of where that water is going to move, both natural and human impacted systems. So, vegetation impacts drainage, right? Impervious surface prevents infiltration. So figuring that out is a key component to all of this. And I think Topobathymetric Lidar can help map these areas and provide elevation data. And I also think that the stuff that we're doing here, we have teams developing, training data and refining data, right? Extending these models to Topobathy. And that's kind of where I want to take a quick turn to, extending this underwater. And so here is a project for Lake Tahoe that we flew Topobathymetric Lidar for and provided. This is the monitoring plan for Lake Tahoe done by the Tahoe Regional Planning Agency. And the next few slides, shout out to Shane Rosmos and Chris Parrish for providing these. And really, they're going to map aquatic vegetation, and they have a lot of data sets, and you can see Topobathy is one of them. And also not on here is they also had a lot of diver data sets. So they went out with scuba gear and actually collected a lot of detailed information about everything out there. So the LiDAR itself, these 3D structural characteristics can help determine something from like is it a patch of vegetation that might look like in a photo, or is it a rocky outcrop that's also making that color kind of pop. So helping to characterize it from that respect. And the reflectance. So I talked about normalized reflectance, so you can help have the contrast of like features. And I think this is a great example of that, where Topobathy can help out in photo interpretation, especially on lake edges where there's a lot of overhanging veg and trees. You don't see it, you can't map it. In the LiDAR, it's coming out. You can see where it is. Here, it's blended in with the shadows. So it can help out in all sorts of situations and also add to all your segmentation routines. The end result, you're increasing your accuracy of your aquatic mapping, better monitoring plan, better management. There's invasive species out here you can target and mitigate. So I'm almost there. I wanted to cover relative reflectance normalization. I think conceptually I just talked about it, how we want a coral that's 1 meter deep underwater to look the same in the reflectance image as if it were at 5 meters deep. and not get darker because the laser is attenuated. So you can train those patches and make that correction. But I do want to point out that, you know, we're still looking into this. We're doing this standard on NOAA projects now, but there's a lot of variables affecting this. That I'm looking at solar radiance, spot size of the system itself, pointing angles, like is the receiver aligned properly? That can have an effect. And of course, turbidity, I think, is one of the biggest drivers. We'll see water conditions change along a flight line, from mission to mission, and even within the water column itself. So how do you characterize and properly model that to produce the best image? And then finally, you know, this is just a Florida Keys, really just an example. This is a reef track habitat map I pulled from Fish and Wildlife, and I just wanted to cycle through some of the data layers. Just kind of a stretched out version of the imagery to kind of tease out where features might be. I'm going to keep the polygons on there. Then we're going to look at the topobathymetric reflectance, and you start to see a discrepancy in accuracy on what you might be able to map. And that has a lot of impact for monitoring plans that need certain amounts of vegetation. I also think multimodal, coming back and remapping things, you can help tease out, you know, seagrass from kelp and do that movement there. So I think it's pretty valuable stuff in that when it's going to come to benthic habitat mapping. So this is the end. I know I'm a little late, sorry. You know, aquatic systems are more dynamic. I guess I just stressed that one more time. Flow events change things drastically. And long-term monitoring networks, you know, how do we say, if we're going to do this and map everywhere, you know, we don't want to go mobilize and try and get data and have it fail or have to go on standby. It's really costly to do that. So you need to kind of, you want to mobilize once and get it on your first collect. And to do that, you know, can we put NTU stations on more USGS gauges? We have turnaround of the KD product that Mike and others have alluded to using that. I bring up webcams. I mean, honestly, the first thing that when we get a request to map a river, we go into Google Earth and just look at the geotagged photos of the stream, any ones we can find. You come across a lot of interesting stuff, but you can sometimes get an idea of the river system. But if we had more webcams set up, you know, directly on water conditions, we can also look at that way. And then change detection. I think I hammered that a little bit. Maybe no pun intended there, but that's going to be important as we build these standards and go out for recollects. And I guess as Topobathy, I always like to say, you know, depth expectations and you know, do you need to get every full coverage of the color mission to success? And if not, how are you going to do like the sonar or a transect to fill in that gap? Is it even possible? And all this obviously is, I think the late great Sean Connery once said, map once, used many times. And so I think it's going to be more like map a bunch, use a boatload of times, but really that's the goal here. And you can save money and time if you do all this correctly. And I'm sorry I went over, but that's all I got. So thank you.
All right, thank you, Colin. We very much appreciate that. We don't really have time for questions. So if anybody wants to get in touch with Colin, you can feel free to do so directly.